Good morning, everyone, and thank you to the organizers for inviting me to speak today. It's a great opportunity to talk about an emerging issue across the northern Great Plains, and that is soil acidification. And it is something that we have not historically talked about as a soil fertility issue because throughout much of this region, we've always just figured we have high pH soils, that's what we're trying to manage. Well, over the past 5-10 years, we're starting to realize we got these little areas here and there that have some problems with acidity. So we're going to address some of that today. Of course, now I always want to mention where I work. It's my shameless plug for 30 seconds. I work at AgVice Laboratories. We're a soil testing lab that covers the northern Great Plains and Canadian prairies. And we've been doing this for, well, over 45 years now. I work at our Northwood, North Dakota location, which is just outside of Grand Forks. We also have another lab in Benson, Minnesota. Here's a look at what the inside of the lab looks like. If you do ever get up to Grand Forks, this is my open invitation to everyone to stop by and get a lab tour. It's always great to show people what goes on inside a soil testing lab, what happens when that soil sample comes in, as it gets processed, and how all these different instruments you see here do something different. And whenever anybody comes to tour a lab, I mean, whether it be our lab or anybody else's, nobody ever says that it was less than they expected. There's always more going on. So it's really cool to show that to people. And the best way to do that is with a lab tour. But we're not going to talk about all that today. We're going to talk about acid soils. And the reason why is we're getting a lot more questions about them because these acid soils are becoming more common. Can I let my coffee camp out with you over here? It's warm. I see you got your coffee, so you'll be good. Just don't drink mine. So one of the reasons we are getting a lot more questions about acid soils is, one, we just have a lot more acid soils that we're starting to encounter. And part of that is because of precision soil sampling. We have a lot more grid and zone sampling happening across the landscape. So we are starting to find these low pH pockets inside of fields where historically, when we are just whole field composite sampling, the high pH and the low pH areas of the field would get all blended together in that soil sample and everything looked fine. But now we're starting to break that out and we're starting to find and diagnose some of these more problematic areas of the field. Another thing that we do at AgVice is we test the the subsoil sample that comes in for pH as well. And sometimes we see acidic subsoils. That prompts questions. And we also offer buffer pH tests on any composite test. And occasionally you'll see pHs at the surface that are below 6. And that's kind of the point where we start talking about lime applications, or at least people in the eastern Corn Belt and east of here would be talking about a lime application. And when folks around here start to see that and they see a lime guideline printed on a soil test report, that prompts a whole line of questions that we never ever used to think about. So these are some of the things that are happening more commonly and why we're talking about it today. So first of all, let's just cover what is pH, just pH in general. And what it is a measure of the activity of hydrogen ions in the solution. That solution could be water, it could be the soil solution, it could be the pH inside of a plant. And why we care about pH so much is it is a master variable in chemistry and biochemistry. It covers many different reactions. It affects the speed that reactions happen at. It affects the availability of certain nutrients. And so soil pH in itself, being a very simple thing, just measuring hydrogen ions, has a big control over many different processes that happen in any natural system. Now, pH is measured on a logarithmic scale, so that means for each pH unit increase, it's a 10-fold increase. So the difference between a pH of 6 and a pH of 7 is a 10-fold increase in the number of hydrogen ions dissolved in the soil solution. So even though you might see a pH of 7 or 8 and it doesn't seem that different, it actually does mean a lot for soil chemistry. Now, a neutral pH is measured right around 7, and many of our soils range anywhere from 6 to 8, kind of in that neutral to slightly acid to slightly alkaline side. But today we're going to be talking about what happens when soils get below 6, down into that 5, and in some cases into that 4 range. So soil pH, we kind of generally classify it with these values as you see in the table. Right around, say, 6.5 to 7.5, that's going to be my very general neutral category. Things are generally honky-dory there. And for our friends in the room that have mostly calcareous or alkaline soils, and you get into pHs around 7.5 to 8.5, we consider those alkaline or calcareous. And when we talk about fertility management, that's where we really start talking about banding fertilizer, phosphorus in particular. If you're growing corn, maybe apply zinc. You know, those are some of the principal nutrient issues there. If you get above 8.5, probably an indicator that you have a sodic soil and you have a sodium issue that needs to be addressed. Now, when you get below 6.5, somewhere in that 5.5 to 6.5 range, depending on the crop you grow, liming might be necessary. And that's where crop choice becomes, or starts to become important. But when you get pHs that are less than 5.5, this is kind of that very acidic range where aluminum toxicity becomes a very serious management concern, and liming becomes a very important discussion. And when we're talking about liming, we're not talking about 50 pounds of lime or 100 pounds of lime. Soil pH, we're talking about changing bulk soil properties. So that's where spreading lime is done in terms of tons of product per acre. Usually 1-2 tons. Sometimes it might be on the order of 4 to 5 tons, depending on how acidic that soil starts and where you want to get to. So I put this slide up right away just to make sure that we all kind of have this concept that liming is actually a really serious business. And that's why we're going to focus on it quite a bit today. Now, I do like to start off with kind of giving a context for why we haven't talked about liming so much. And this map kind of generally splits the United States in half with the regions that used to, or we'll say traditionally, applied lime. And a lot of that is the eastern humid United States. Old pedologists would refer to these soils as the pedalfers. And this is where we find highly weathered soils where calcium carbonate has been long leached away and is just a fond geologic memory. When you get kind of west of, roughly here is maybe the 95th or 96th meridian, pushing westward into the Great Plains, the old pedologists would call this the pedocals. The cals referring to calcium carbonate in these rather young or arid soils where the naturally occurring calcium carbonate has not been leached away. Now, this map was put together back in 1941 by the pedologist Hans Jenny, but since then, there has been lots of changes across our landscape. And one of those changes is the number of acid soils that we're actually finding out on the landscape. And this is a look at our AgVice soil test summary data from this past fall in 2022. And in each of these regional zip code areas, we've classified the percent of soil samples that are below 6. So this is that point where we start having this liming discussion. And as you can see throughout much of central South Dakota, anywhere from 15, 16, 21% of soil samples are actually below 6. So this is actually a pretty prevalent issue. And if you look into southwest North Dakota, we got about 14, 16% in the Dickinson and Bismarck areas. So it is kind of very much a western area issue that hasn't been affected by the most recent Wisconsinian glaciation that was about 10 to 13,000 years ago. Also in north central Montana, another place where this is happening. And a lot of this discussion is occurring in these long-term no-till areas. We'll discuss that in a little bit. Now, to give you a little context for how we've been looking at this issue over time, this is kind of the same data, but now we're looking at the trend going back about 20 years. To, I guess, that'd be 1998. And here I have it based on the zip code areas. So we've got Aberdeen, Pierre, Mobridge, Bismarck, Dickinson. And you can see that over time, that we just see the number of soils that are testing below 6 goes up and up each year. And this is largely because of precision soil sampling and actually being able to find these areas in the fields over time compared to whole field composite sampling that would have been more common 20 years ago. All right, let's talk about this role of soil sampling just a little bit more. So historically, with whole field composite sampling, a sampler who's doing a good job is trying to sample kind of the mid-slope representative parts of those fields. A good sampler is going to avoid the sandy ridge. They're going to avoid the saline area because they don't want these non-representative areas of the field to skew that soil test result. And as a result, some of these saline areas and sandy ridges and eroded hilltops are missed in a typical whole field composite soil sample. But with precision soil sampling, we're actually actively going out there and trying to soil sample these areas because we're actually going to try to manage them with variable rate applications. So whether it be grid sampling where you're just regularly creating a grid, or looking at zone samples where we're actually breaking up these areas, we're actually starting to sample these sandy ridges. We're starting to sample these saline areas. So we are finally starting to uncover some of these areas, and we're going to try to manage that variability. To give you an idea of what the variability in soil pH looks like, this graph looks at grid sample data, and it actually came from a researcher friend, Brian Arnall at Oklahoma State University. And he had a bunch of grid sample data, and he took the field average within that field, and you see that on the x-axis. And then on the y-axis, that covers the number of grid cells, the percent of those samples within the field that were below 5.5, so kind of where we're starting to think about really acid conditions. So if you have a field average around 6, and we follow up this little orange line, about 20% of the grid cells within that field were below 5.5. So that's if you have a field average of 6. Now, for those of you in the room who have field average pHs around 5.5, there we're looking at around 50 to 60% of those grid cells that are in that field that have a pH less than 5.5. So this gives you an idea of if you have a whole field composite average around 5.5, you're going to have areas of that field that are higher than that are going to be fine, but you're also going to have some areas of that field that are much less than 5.5 and are going to require some degree of management. To give you a look with some more regional data, this comes from our soil testing database looking at zone sampled fields. And here what I did, this is data from 2021, so previous fall, across 33,000 precision sampled fields from this region. And what I did is I first classified these fields based on the number of zones within the field, whether it was a 3-zone field, 4-zone field, 5-zone field, etc. And then what I did within each of those fields is I took the high testing zone and the low testing zone in each field and subtracted those, so I got the range. And then I took the average across all those fields. So it's like the most average of average look at field variability. And if we look at a 3-zone field, we can see we got the data for nitrogen, phosphorus, potassium, but we're going to look at pH. And here we see there is an average pH range of 0.59. So over a half a pH unit is the typical average if you have a 3-zone field. But if you continue to increase the number of zones per field, you go to a 4-zone field, 0.74, 5-zone field, 0.88. If you go all the way up to an 8-zone field, which actually are more of those in north central South Dakota than other parts of the region, I can assure you, you have an average pH difference of 1.35 within the same field. So as we utilize precision soil sampling, we're going to start to uncover a lot more field variability. So like if you look at a pH of 1.35 with just being the average range, let's like actually put some numbers to that. So on the high end, you know, that might be a pH around 6.3. Not too concerned about a pH of 6.3. But there's also going to be an area in that field that has a pH of 5, and that is a serious concern. So just kind of get that idea of variability in your mind. Okay. So that's a look at kind of the extent and also the variability question. But you know what we really haven't talked about yet? Why we're really concerned about acid soils. And there's kind of 2 primary reasons for me as a soil scientist, but there's a couple other reasons we can talk about as well. The first reason is reduced nutrient availability. And typically when we're talking about low pH soils, the first thing that we think of is phosphorus. In this graph, I'm sure people have seen this many times before looking at nutrient availability across this pH spectrum. And when you get to a pH less than 6, phosphorus starts to become less available. And that's really one of the principal things that we're concerned about. But there are other nutrients like potassium, sulfur, calcium, magnesium. A lot of these nutrients are less available in acid soils. Another reason, and really the bigger reason why we're really concerned about acid soils, is aluminum toxicity. So when you get less than a pH of 5.5, especially down towards like 5.0, 5.2, aluminum starts to dissolve in soil and actually becomes a available to plant roots. Normally, it's locked away in soil minerals and doesn't interact in the soil solution. But when you get down to about 5.2 and so, that's where aluminum becomes available. And aluminum is extremely toxic to plant roots. And what happens is you end up with these short little stubby root systems. And these short little stubby root systems, they're not very good at taking up water. They're not very good at taking up nutrients either. So that's why aluminum toxicity is really the big issue. We have many different crops that have different pH tolerances. And this is a look at some of the, I would consider them more Great Plains crops. I'll admit this graph doesn't have corn or soybeans on it, or even sunflower. But as you can see, as soil pH gets lower and lower, the relative crop yield of many of these crops, like barley, wheat, peas, lentils, alfalfa, starts to go down. Our legumes are generally some of the most sensitive crops. So something like alfalfa actually starts to lose yield somewhere around 5.7. Once you kind of get below 6, it really starts to drop fast. Lentils, peas, they start to drop off sooner. Our small grains tend to be a little bit more tolerant. But you'll notice there's also a difference between this orange line and this green line, a wheat that is tolerant to acidity and a wheat that is susceptible to acidity. So there's even variety differences in soil pH tolerance. We'll talk a little bit about that more towards the end of the talk. Now again, to look at aluminum toxicity, why this is so important in especially no-till systems is if you have surface applied urea, and we get a lot of the acidification right near the soil surface, if you have low pHs that are in the low 5s getting into the 4s in those top 2 inches, aluminum toxicity really knocks back a germinating seedling. And this is a look at aluminum toxicity in wheat. And if you have no aluminum, you get these really nice roots, but as you can see, they introduce aluminum, they get these smaller and smaller short stubby roots. And that's why this acidity problem is very sensitive to seedlings, because we're putting our seeds in those top 2 inches in most cases. And they're kind of getting right into the hot zone of where the acidity problem is. Here's a look at some yield data in relation to soil pH. When we get down to about 5.2, you'll notice this line with exchangeable aluminum starts to come up on the graph. That's also the point where we see the grain yield in this study just drops, kind of around that 5.2 range. So that's kind of really this critical threshold where you can kind of nudge your way, getting a little bit lower year after year, but then you hit this line and things just crash right away. So here's another way to look at it. This is a photo I took in Alabama. Again, southeast United States, historic cases of soil acidification, but that's kind of related to their rainfall, parent material. And this is at Auburn University with the colors rotation, and this is a long-term soil fertility rotation, the second longest such experiment in the United States. And this particular plot has not had a lick of lime since 1911. And the soil pH, at least in 2004, was at 4.7. And as you can see, they're trying to plant corn, but there's no corn at all. So I really want to emphasize that this effect of aluminum toxicity can take plant stands to nothing and can take yield to nothing as well. All right, so that's kind of a case study in like, what is the problem? Now, where are these sources of acidity? Now, one of the first things to recognize is that rainfall is naturally slightly acidic. It is in equilibrium with carbon dioxide dissolved in our atmosphere, which makes carbonic acid. So rainfall is naturally slightly acidic. Not really acidic, but just a little bit. And in areas farther to the east that get more rainfall, they're going to have more rainfall and more leaching potential that is going to create greater acidification. We're kind of on this cusp in the Great Plains where we get some rain, but it's not a lot. But of course, as you move farther to the east, that drive for rainfall in the acidification story gets stronger. Another source of acidification is crop nutrient removal. Whenever we remove base cations from the system, and that would be nutrients like calcium, magnesium, potassium, when we remove those base cations from the system, that leaves behind acidic cations like hydrogen and aluminum from the system. So just with the balance there, it tends towards net acidification. And if you are in a forage or silage system, you're removing a lot more base cations, a lot more calcium, magnesium, and potassium in those forages year after year. And so that's where you'll see a faster acidification in forage systems and silage systems than if it's just grain production. One of the big ones, and it's the reason why I have it bolded, is nitrogen fertilizers and manure, or just any source of nitrogen in the environment that undergoes nitrification. So nitrification is the process where ammonium ions get converted to nitrate. And this is a natural process that soil bacteria do all the time. Whether you apply anhydrous ammonia, urea, ammonium sulfate, even the ammonia in MAP and DAP, your phosphorus fertilizers, soil bacteria are going to take that ammonia, convert it to nitrate, and in the process, they strip off a couple hydrogen ions, and that produces acidity on the backside. And this is really kind of the big driver of acidification over the long term, especially as nitrogen use has gotten greater and greater over time. Another source of acidification on the fertilizer side is elemental sulfur. Anytime you add elemental sulfur, soil bacteria will oxidize that from sulfur to sulfate, and that actually produces 2 hydrogen ions per each atom of sulfur. And I do want to recognize the elemental sulfur-containing phosphorus fertilizers. Mosaic's Mez product is probably the most commonly known one. Anytime they are adding elemental sulfur, that is going to be an acidifying one. I'll admit Mosaic's isn't the only one out there. There's a lot more elemental sulfur products like that exist now. So that's on the fertilizer side. We also have to recognize that plant residues do some acidification as well. If you have decomposition of plant residues that create organic acids, that is also a source of acidification, and a lot of those organic acids are concentrated near the surface, especially in a no-till system. So again, coming back to this nitrogen part before we look a little bit at the stratification question, this is some work out of Kansas looking at annual nitrogen application for 40 years, continuous and application. And it was in a no-till system. So they have a range of fertilizer rates. These are in kilograms per hectare, but it's roughly about the same as pound per acre per year. And at the lower use rates, you see that this push of soil pH at the soil surface isn't really great, but you notice as you get to a higher and higher N rate, it does push a little bit towards the low pH. Where you get to this biggest N rate of around 200 pounds of nitrogen per acre per year, you get this big push towards soil acidification at that surface down to 4 compared to all those other fertilizer rates that are somewhere in the 5.5 to 6 range. So this graph really demonstrates that if you overdo nitrogen application, you can really push that acidification part because you are applying more nitrogen than that crop actually needs and you acidify it all that much faster. And of course, in a no-till system where we're not mixing up this acidity across the whole tillage depth, it starts to concentrate at that surface. Now this is a surface application, but if you happen to be banding fertilizer, urea or anhydrous at say 4 inches, that's where you would see this bulge. So it's wherever you place that nitrogen in the system is where you're going to see this. Now let's put some numbers to it, just to kind of quantify it and not scare everybody at the same time that nitrogen is the devil, because we're not going to remove nitrogen from our systems because we still want to grow good productive crops. So here's a scenario that I kind of just slapped together with annual fertilizer application of 180 pounds of nitrogen, 40 pounds of P2O5. I'm going to skip the potassium part because it doesn't really cause any acidity, and 10 pounds of sulfur. And I think it's a pretty plausible fertilizer rate if you're trying to grow 150 bushel corn or 70 bushel wheat. And now the question is, how much acidity does this particular fertilizer blend create over time? So I put together a rate looking at urea, MAP, 1152O, and ammonium sulfate with these different fertilizer or these different nutrient targets, what that means for fertilizer rate, and any of the nitrogen in these fertilizers, because it goes through nitrification, is going to create some acidity. So at these target rates, urea creates 3.6 pounds equivalent of a calcium carbonate equivalent. That's how we measure acidifying potential. We measure it as how much lime would I need to add to neutralize that acidity. So the nitrogen in urea is 3.6 pounds per pound of nitrogen, and then for MAP and AMS, it's 7.2 for both products, so they act the same. So I added up what would be the 1 year equivalent of acidifying potential at this fertilizer rate, and that equals about 770 pounds of calcium carbonate equivalent. Now in a single year, okay, 700 pounds per acre, not super crazy, but over a decade, if you applied this rate every single year, at this point we're ignoring legumes or anything else in the crop rotation, we're just gonna look at this scenario straight from a annual nitrogen input standpoint, it ends up adding to about nearly 8,000 pounds of calcium carbonate equivalent over that period. Now, for those of us who are trying to manage these acid soils, this is something important to recognize, and it highlights that if you're going to be worried about long-term acidification management, we really do need to be smart with our nitrogen management and not overdo it in any given year. We got to utilize tools like soil testing, taking credits for our previous crop legumes when those are applicable. Now, for our friends in the room that have high pH soils, now here's a little bit of bonus information why you can, not get so worried about this at this moment. So for our high pH soils, and those would be any soil that has at least a pH of 7.3 or greater, you're going to have some amount of calcium carbonate present in that soil. And for each 1% calcium carbonate equivalent in your soil, that is going to equal about 20,000 pounds of naturally occurring lime at the soil surface. So that serves as a really big buffer for you to work with nitrogen inputs like this that are going to cause some acidification, okay? But for those of us that don't have that benefit of having calcium carbonate at the surface, we have to be really smart about our nitrogen management and start to recognize what our lime budgets are going to look like in the future. Now, on the aspect of soil pH stratification and tillage, this is where the no-till story really comes in. In a conventional tillage system, we are constantly tilling our soil in the surface, and we are mixing and distributing that acidity throughout the whole tillage depth. The other thing that happens in a conventional till system is we still have erosion going on. So if we have higher pH soil with some naturally occurring lime down in, say, the 6 to 12 inch depth, and as we lose an inch of soil on the surface, every decade or so, when those cultivator shovels come through and they start to pick up some of that high pH soil from below, you're kind of refreshing the system with a little bit of natural carbonate below. Meanwhile, you still have other nutrient loss issues, but that's one reason why we don't see these acidification things so much in the conventional till system. It's kind of the ongoing erosion, quote unquote, refreshment story. But in no-till, we don't have that. If we apply urea at the surface, we start to get a big pH depression. So here in this scenario, you have like a pH of 5.2 right at the soil surface. But below that, we don't touch that subsoil area down at 5.6, and we never ever get those carbonates back up into the system from down below. So that is why our no-till systems tend to get this stratified scenario, and why we see greater issues with aluminum toxicity, especially for seedlings right up near the soil surface where we're putting those seeds. Here's a look at low pH on the landscape. So this is a picture from north central Montana. If you've ever been in a wheat field, you usually see the really good areas kind of have this golden stubble concept, and some of these less productive areas of the field kind of have some browner stubble. It's really tough for you to see this up here, but it might be a little bit more clear in your handouts. On the hilltops here, this is where the golden stubble on the field happens to occur. And this is the area where typically we have erosion and there's carbonates that are in that top soil. And we typically would think the hilltops are going to be the less productive parts of the field, right? Well, in this case, the brown stubble where there's less productivity is actually occurring on the downslopes and the flats. And these are the areas that get more soil water. They have better soil organic matter. Because they have more organic matter, there's also more nitrogen mineralization. So coming back to that nitrogen use efficiency question. And also there's greater crop removal that has historically happened on these downslopes and flats. And so this is an example of a field where the typical areas that we would think about being the most productive are no longer the most productive parts of the field. Here's a look at aluminum toxicity in southwest North Dakota. This is right near Reeder, along the North Dakota-South Dakota border. This is looking at safflower. On the left, these are the good safflower plants. If you put on your bifocals or your binoculars, you'll see these little tiny plants right here on the right. These are the poor areas. They had very poor safflower germination, very poor stands. In this photograph, this pattern kind of follows the landscape. The agronomist went out and soil sampled in these areas and took stratified soil samples at 0 to 2 inches, 2 to 6 inches, and then at a 6 to 12 inch depth as well. In the good areas, the top 2 inches had a pH of 4.5. For all of us, this should be a big shock that the good areas had a pH of 4 or 5. But in the 2 to 6 and the 6 to 12 inch depth, it was at 6.1. But where it was bad, really bad, pH in the top 6 inches was 4.3 and 4.6. We also ran aluminum on these soil samples. In the bad areas, the top 2 inches had 91 parts per million of aluminum. That is absolutely screaming. Even in the area below, 25 parts per million of aluminum. That is a lot. For any soil that doesn't have a pH problem, this aluminum value should be near 0. There shouldn't be any aluminum out there. So this is what it can look like when you let a pH problem get too far out. If that case isn't enough for you, this is a look at sunflowers south of Dickinson, North Dakota. A photo shared with me by Ryan Beto at the NDSU Extension Center out of Dickinson. He had a drone. He was working with a producer with a bad sunflower stand issue. You can see on the left, pH of 3.9, he went out and sampled that. First of all, let's just be shocked that there's a 3 in front of that number. Those do exist. But on the right, you see you got a pH of 5.1. So as far as sunflower stand goes, kind of the threshold for sunflowers is, we'll say somewhere between 4 and 5. But we already know that this sunflower stand on the right is probably already losing some yield at a pH of 5.1. There's some aluminum that's there. Also got questions about herbicide activity as well, because we know pHs are very important for herbicide breakdown. So we have to think that this is a really extreme case, but this story at 5.1 isn't good either. So as we try to think about how to diagnose some of these issues, get questions about how do we soil sample them? And I think the first part is being able to identify the problem, to actually know what is going on in some of these problematic fields. Because often we think we got salinity issues, we have other nutrient issues, we have erosion issues. In this case, we got to identify that our problem at hand is a pH issue. I think that often happens with in-field troubleshooting. Somebody gets a phone call, I got a problem in my field, want to come out, take a look at it. Often with soil and plant analysis, we can kind of figure out that it actually is a pH issue. Another place where we can see issues is yield data. Look at yield monitor maps year after year and you go, these areas just never seem to produce very well. And often people think it's just because it was not a very thrifty area of the field, just not a great producing area, but now we've been able to identify some of these areas as having a low pH problem. Another way that I think we can really identify them is with zone soil sampling, with our typical soil sampling depths at 0 to 6, 6 to 24. If you have any zones in the fields that are testing less than 6, we've got to take a look at those. Also, if you have any subsoils that have a pH less than 7, where we have an acidic subsoil as well, got to take a closer look at those. So what does that mean, taking a closer look? Well, I think one of the first things to do is when we typically zone sample, it's often still 3-zone fields because you got a low, medium, and high yielding part of the field, right? Most people can at least identify 3 zones in a field. But in some of those zones, they're still really big. They could be 40 acres, 60 acre size zones. And so we got to do a little bit of refining to actually pinpoint where we're going to think about applying lime in these fields. And so that's where I think we got to refine some of these zones with satellite imagery. That's a particularly useful tool because where aluminum toxicity starts to occur, it's going to take those plant stands down to nothing and you have very little plant biomass. So satellite imagery is really good about picking that up. So you can at least draw some finer zones with satellite imagery or grid soil sampling at times. I'm mostly a zone guy myself, but when it comes to pH management, sometimes grid sampling might be needed at 1 or 2.5 acre grids at the very largest. 5 acre grids, much too large to actually capture anything. I think you got to be at least 2.5, if not 1 acre grids to make a good lime map. Then what we do is we resample these reef-defined zones or grids. You're going to want to test them for pH, buffer pH. Buffer pH is the actual test that we do to figure out how much lime needs to be added. Other things like cation exchange capacity, organic matter, aluminum are also helpful pieces of information. I think the 0 to 6 inch depth is the most practical depth for soil sampling in these refined scales. It's also what the lime guidelines were developed for. But if you do have some stratification issues, a 0 to 3 or 3 to 6 inch depth is a good idea to figure out if you have a stratification problem to start with. Not everybody does, because sometimes that whole 0 to 6 inch depth is acidic. Sometimes a 6 to 12 inch depth is also very informative if you have a history of deep banded anhydrous or urea. And after we've done all that work, we can put together a variable lime rate script. Keep it cheap is kind of my general thoughts, because you're going to be hauling out tons of product out to that field. And for many of us in North Dakota, South Dakota, we don't have a lot of lime sources. We'll get to that in a second. But because the transportation cost of the lime is going to be a big part of that budget, I always like to remind folks to keep it cheap, don't get fancy. In some cases, an on-off rate might be the most practical way to go about it. All right. Now let's actually talk about what liming does. And it is a process of raising soil pH. And this reaction here is what is happening when we add lime to the soil. So we add lime, called calcium carbonate. We have our hydrogen ions here that react with this calcium carbonate. In the first step, those hydrogen ions, when they undergo this reaction, create water. The next step, the lime, the carbonate portion here, creates carbon dioxide. So it is the carbonate part of this lime that is actually neutralizing the soil acidity and increasing soil pH. It is not the calcium part of the lime. There are other lime sources such as dolomitic lime, a magnesium carbonate, that are still good lime sources, but it's not this whole calcium story. I want to clarify that right now because we get questions about, well, I actually got a bullet point here, about using gypsum as a liming source. Gypsum is not a lime source. It is calcium sulfate, and it does not contain calcium carbonate, and that is why it is not a lime source. It doesn't change soil pH. And lime can add calcium if you do have like a true calcium nutrient deficiency. They're not very common. Actually, they're not very common at all across this region. Even our most acidic soils tend to have enough calcium to actually provide decent calcium nutrition, but they don't have that carbonate. That is the really key thing that I want to emphasize right here. So what are our lime sources? Well, traditionally, egg lime is what is used, and that is mined and crushed. I have crusted limestone. No, they crush that limestone. And egg limestone comes in two flavors. There is calcitic limestone, which has less than 5% magnesium, and then there's dolomitic limestone that has greater than 5% magnesium. Depending on which source you have is usually just based on what is locally available at a quarry. There's also pelleted lime, which is a very fine ground egg lime that is then pelletized. You'll see this product kind of coming out of Iowa, most likely. It's our closest source. There's also a couple byproduct sources that are very important to talk about, and that is sugar beet spent lime. That comes from any of the sugar beet plants that are scattered through the region, as well as water treatment spent lime. Some cities have a lime softening process in their water treatment plants, and they use a very high-grade reactive lime to soften that water before it goes into the city, and that leads to byproduct spent lime on the other side. Now, no matter what lime source you have, the liming quality will be measured as effective calcium carbonate equivalent, ECCE, or effective neutralizing power, ENP. ECCE is more commonly used in Iowa, Nebraska as a lime quality unit. In Minnesota, they use ENP. I mention these things because South Dakota, North Dakota, or Montana has any lime quality laws. So we got to borrow from the folks to the east. And the quality is important because that will adjust the rate for the material's purity and fineness. So here's a look at what these sources look like. Regular egg lime, crushed limestone, generally it's pretty cheap, but we don't have any local sources nearby, so it gets to be quite expensive to haul in. Pelletized lime, this is again crushed limestone that then gets pelletized. It's a very expensive product, generally about $200 a ton, depending on how far they have to haul it. I mean, it is a very nice product to work with because it has been pelletized, so it kind of works like a regular fertilizer. But again, we don't have any local sources. The closest sources are going to be in Iowa. And then spent lime, whether it be from industry or a water utility, it's very cheap because a lot of these places just need to get rid of the lime. We do have some local sources, but it is a difficult product to handle because it is a wet product. Often the water contents range anywhere from 30 to 50%, so it's expensive to haul because you're hauling water. But since it's wet, it's also kind of this weird chunky material at times, and you need to have special spreading equipment. You're not going to run that through a floater at all. You generally have to have some special spreader boxes or a manure spreader. Usually the ones with the vertical beaters are a little bit better for trying to fling out some of this material. Also, I've known some people put like cyclone spreaders on the back of a manure spreader to help fly some of that manure out as well. Not the manure, the lime out as well. So requires some specialized application equipment. Now, any of the fine grind lime sources, they're going to react much faster and raise soil pH at a quicker rate. So any of these products like pelleted lime or spent lime, these are very, very fine products to start off with. Egg lime depends on how coarsely the quarry is going to grind that lime. But the finer the mesh, so the smaller the particle size with any lime product, the faster it reacts. So that's a good thing. Now comparing these lime sources, this is some work out of Iowa that Antonio Malorino did, looking at different lime rates in some of these lime sources. So we got egg lime, reagent grade calcium carbonate, and pelleted lime. And you'll see both in corn and soybeans, these products act the exact same. So the type of product you work with isn't that important. It all comes back to the amount of lime that we are using and actually being able to change soil pH effectively. To look at that again, here is the same products measured over time and soil pH. So egg lime, calcium carbonate, pelleted lime again, they all increase soil pH just fine and dandy. But you'll notice that any of the low lime rates, like 1 ton per acre in these cases, just increase pH a little bit. It all comes back to a question of how many tons of product are we actually spreading out there. So how do we actually figure out how much lime to add? There's a couple vocab terms I'm going to introduce here. The first one is the lime requirement, and that is the amount of lime that is needed to raise your current soil pH to a target pH. So what is a target pH? Well, it is that line or that pH that you're trying to reach. And usually that target pH is going to vary for different crops, but we're going to select the most sensitive crop in your rotation. Because if you're liming, we're going to do this at an effective rate to apply it for, to at least make it last 5 to 10 years or so. So when you apply that, you want to make sure that you have it tailored for the most sensitive crop in your rotation. For most of our crops, a pH of 6 is just fine. For some of the more sensitive crops like alfalfa, clover, perennial legumes, we would want to raise that pH up to 6.5. And that buffer pH test that I mentioned earlier, that is what actually measures that soil's buffering capacity, that soil's ability for you to increase its pH with lime. And after you run the buffer pH test, it's going to tell you how much lime to add, and then you will adjust that final lime rate for its quality, again based on purity and fineness. So this table looks at soil buffer pH. If you have a buffer pH test at, say, 6.6, and we want to reach a pH of 6, it calls for applying 2,000 pounds ENP, that's the lime quality unit, per acre. Now, most typical lime sources have an ENP somewhere around 1,000 pounds of ENP per ton. So, if it's 2,000 pounds, and typical egg lime is going to be about 1,000 pounds per ton, that means you're going to be applying about 2 tons of lime per acre. Now, if you have a really acidic soil that calls for more lime, you'll have, say, a pH of 6.2, calling for 4,000 pounds. That means there'll be about 4 tons of lime required per acre to increase that pH to 6. So again, that's where I highlight that we are spreading lime in tons, in terms of tons per acre. These aren't small rates because we're really trying to change a bulk soil property here. Another important thing to mention is the role of subsoil pH. Now, many of you who have ever seen a lime recommendation appear on an egg by soil test report, if you read down in the comments section, you might see this little asterisk that says, for western Iowa, western Minnesota, South Dakota, North Dakota, that you can cut that lime rate in half. And this graph is the data behind that comment. But it comes with a nuance, and why we got to look and talk about this a little bit more. So, if you have an acidic soil pH and an acidic subsoil pH, your chance of getting a lime response is going to be much, much greater because those plant roots, when they get started, if they have to grow through an acidic subsoil as well, they have a difficult time their entire life. But if you happen to have some lime down in the subsoil, maybe starting down around 12 inches, those plants, they can actually access some higher pH hospitable soil later in their life. And so they kind of have an easier go of it, but they need some help to get started. So on the left, this is a look at lime response across a range of soil pHs from an initial pH if you have a high subsoil pH as well. So you'll notice that there's a little bit more variation in these bars looking at relative crop response. But if you have a low subsoil pH, it's a pretty sure bet that you're going to get some really nice lime responses when you put some out there. So this is why, if you have a subsoil pH that is high, then it is often reduced by half to account for this subsoil calcareous high pH material below. Now let's look at the map of where we see this. Now you'll see, now this is a map looking at subsoil pHs below 7. Now throughout much of central North Dakota, or central South Dakota here, you notice that that happens to be the spot on the map where we have more acidic subsoil pHs. So that means that these are some of these areas that we're going to still be using a full lime rate to actually maximize our crop response to lime application. So if I remember the map before, it was about 15 to 20% of the soil samples in this area had a topsoil below 6. So these are the same set that has a subsoil below 7. So that means about half of the acid soils that we're running into this area also have an acidic subsoil. Okay? Now there we've talked about the extent of the acid soil issue. We've talked about the problem, why we need to address it. We've talked a little bit about soil sampling for it. We've talked about what liming does and how to figure out a lime rate. This leaves a very big question left. Now, where do you actually find lime? Well, one of the best resources is the Minnesota Department of Ag actually has a lime analysis results page. And you can just Google this page. And Minnesota has lime laws, so they actually put together a resource for this. In South Dakota or North Dakota, we don't have lime laws, so we don't have a really cool resource where they've put all of this information together. So I've kind of hazarded to guess to put together a map here of where we actually can find lime across the region. And I have divided it up based on limestone quarries, areas where you can get spent lime out of industry, and any of the municipal sources where you can get water treatment lime. Now first is the quarries, In South Dakota, there is actually a limestone quarry in the Black Hills. I don't know if they're grinding it to a fine enough source to be used as egg lime, but there is limestone quarries down here. There's also one up in Winnipeg. There's a couple around the Twin Cities, southern Minnesota and Iowa. This area has some underlying limestone bedrock, so they can actually mine it. But you notice there's a big part of this map here that is missing any kind of limestone quarries. Well, next, we have those sugar beet lime sources. So all throughout the Red River Valley of North Dakota and Minnesota, down in Renville, Minnesota, also Sidney, Montana. Those are the areas of the region that have sugar beet lime sources. A lot of the lime that's getting spread in southwest North Dakota, as far as down as Lemon, a lot of that is coming out of Sidney. In north central Montana, they also have a sugar beet plant in Billings, so they're trucking that about 200 miles northward to get spent lime up there. If you have areas that have trees and timber logging, like in northern Minnesota, they have access to wood ash. Last I checked, we don't have many forests in either North or South Dakota, so we don't have access to wood ash. There's a couple ethanol plants in Minnesota that actually have lime as part of a processing part. I found these locations. These weren't ones that I was thinking of traditionally, but I found these on the Minnesota Department of Ag's table, and I thought it was worth putting them on here because if you happen to know of any ethanol plants in South Dakota that are using lime as part of a treatment process, that might be a resource worth adding. I did a little bit of Googling as well, trying to find cities that are using lime softening in their water treatment process. And in South Dakota, I was able to find Aberdeen, which I know of people who are liming throughout this region. Seems to be the most popular place to get water treatment lime. But also Watertown, Brookings, Sioux Falls, Vermilion, and Mitchell do have lime softening processes. Now, all those municipalities might not be geared up for hauling out lime, but I know Aberdeen is. Now, trying to find out which municipalities actually have lime is a little bit difficult because you got to spend some time Googling and trying to read through their water treatment web pages. So if you happen to know of any other sources for lime throughout this region, please let me know. I'm always eager to try to fill in this map, but we got a lot of space out here. So that's why the transportation question is a very important thing to recognize. Now we are here at a no-till meeting, so we have to talk about this. Is lime incorporation necessary? In conventional till systems, usually lime is incorporated. One reason is because lime is very slow to react and it doesn't move quickly with water. So if you can mix that lime in the area where you have the acidity problems, it's going to let it react faster. Now in our no-till systems, since much of that pH is constant, or the acidity is concentrated right near the soil surface, if we can target that lime right near the soil surface where the acidity is concentrated, then we can effectively alleviate the low pH and aluminum toxicity problems. But for folks who have been banding fertilizer deeper, and if your acidity problem is located, down around 4 to 6 inches, it's going to take a lot longer for that lime to move down to that depth. We have lots of questions about where that part is, or how quickly it can leach downward. Now, one thing to recognize is that incorporation is going to make that lime react faster. So in a no-till system where you're not doing that, that is going to be a trade-off of that no-till system for trying to manage this pH issue. Here's a look at surface liming with some work out of Kansas in a no-till system, just to kind of give you an idea of how quickly some of this moves. So they applied lime at 0, a half ton of Pell lime, 1 and 2 tons of egg lime, and then they soil sampled every inch going down to 6 inches. And this is after 4 years. You can see wherever they applied lime in the top 2 inches, they do see an increase in soil pH from about 5 up to 6 with a 2-ton rate, but even with a half or 1-ton rate, you get about a half pH unit increase. At the 1 and 2 ton egg lime rates, they start to see a little bit of an increase down to 3 or 4 inches as well. So it just takes a lot longer for lime to move in a no-till system. But if all of your acidity issue is concentrated right near the soil surface, it'll take care of it. Now, to help answer some of these questions going long-term in our region, because there hasn't been any real lime work on it, myself at AgVice, along with my colleague Jody Bowe, who is from Western North Dakota, we installed a long-term no-till trial on her home farm near Beulah. And here we applied lime in a no-till system up to, well, what would be about 5 tons of lime per acre. Initial soil pH was 5.2 and 5.4 at the 0 to 3 and 3 to 6 inch depth. And we installed this in May of 2021. For any of you who have been keeping track of rainfall records, it's been pretty dry since then, so we haven't seen a lot of movement in that lime yet. Here's a look at the soil pH changes at those different lime rates after 1.5 years, and in the top 3 inches, we have seen an increase in soil pH, which is good. It means stuff is doing something compared to the 0, half, 1 ton rate. At the 1.5 to 2.5 ton rates are still kind of right around a pH of 5.5. So far, we haven't seen any increases in soil pH at the 3 to 6 inch depth, but over time we hope to measure some movement down to that subsoil. Well, it's not really the subsoil, it's just the deeper topsoil. And we'll gladly keep everybody updated as this project continues. All right, so that's the discussion on liming. Now, we have to talk about alternatives to liming, because I know that not every acre of the Northern Great Plains is going to get limed. We have questions about owned land versus rented land. You know, how do we try to mitigate with these issues, even though recognizing that liming is really the only true solution to the problem? Well, one of the first ones is being able to identify aluminum-tolerant crop species and varieties. Another thing that can help is higher rates of seed-place phosphorus. I think it's also important that we have to recognize smarter nitrogen and sulfur management, since these are some of the acidifying processes on the landscape. We have to really dial in on our nitrogen and sulfur management to make sure we're doing our best job there to prevent the long-term acidification thing, as well as, in some cases, if we're not going to do any of these things, have to think about alternative land uses. So what we do when we talk about soil salinity management, if we're not going to do anything to manage the acidity problem, well, I ask the same question. So again, look at soil pH tolerance with different crops. Some of our small grains are going to be our best options on these acidic soils. Here's a look at varieties. In the Southern Great Plains, they've been dealing with this issue for a much longer time than we have. In Oklahoma and Kansas, they actually will score and rate varieties for acidity tolerance. This is a look at Oklahoma State's winter wheat variety tolerance trials. In the front part of this photograph, you'll see a bunch of different winter wheat varieties. Some of them look good, some of them don't look good at all. So this does show that if you know what varieties work, it does give you some options, but it only gives you about, say 3 or 4 variety options for managing these acid soils. So we miss out on some of these other potential varieties that might be better suited for disease or yield. This is where we are looking at a defensive variety. I love this photo because in the background, you see where they limed all of these treatments, all these different varieties. And you got beautiful winter wheat stands all across the back. So where we manage pH and can actually lime in these scenarios, it gives us a lot of different variety options to play with. So always keep that in mind. Here's a look at some NDSU variety trial data. Well, it's actually a photo. We'll get to the data in the next slide. That they have just south of town. And on the right is a tolerant wheat variety, and on the left is a not so tolerant wheat variety. You remember what we were talking about before with aluminum toxicity, where you end up with these short, stubby root systems? That's what we see on the left. Where they chose a more tolerant variety, you got much better root systems and much more plant biomass. That's just what a variety can do for you. And here's a look at some of the yield data behind that. They had a Syngenta Soren. They brought in a variety from Washington called Alum. It was actually specifically bred for aluminum toxicity tolerance. They have Minnesota Bowls, North Dakota Glen, older wheat variety, but probably one that many growing spring wheat are familiar with. And then a newer release from Montana State called Lanning. And this one has a parent line of Glen, but it's been specifically bred for acid tolerance. And if you look just by choosing the proper variety, compared to Soren, compared to Lanning, you had an 18 bushel yield response just by choosing the right variety. Now, in good soils that don't have an acidity problem, Lanning isn't the greatest variety. It doesn't have a great disease package. But where you're trying to manage acidity, it does a really, really nice job. All right, here's what I call the Band-Aid option, and that is applying more seed-placed phosphorus. I get questions, can I just put pelletized lime in furrow? Will that fix this acidity issue? Well, that's what you see on the left. 200 pounds of in-furrow Pel lime. In the middle, 50 pounds of triple superphosphate, O46O. Soil fertility researchers like to use triple superphosphate in phosphorus trials because it doesn't contain any nitrogen. So it's easier to balance the treatments across each other. But think of it very similar to MAP or DAP. And then 4,000 pounds of egg lime, or effectively what would be 2 tons of egg lime. Well, you can see applying the in-furrow Pel lime, it didn't address our stand issues. And the reason is lime, again, reacts so slowly that it doesn't actually fix the pH issue in the furrow for that wheat seedling to get started. Phosphorus, on the other hand, is much more reactive, and it actually binds up with the aluminum in the soil and immobilizes that aluminum, allowing that plant to actually get started. And if that plant, that seedling can get started and it can go down deeper and find higher pH subsoil material below, it'll do okay. And it looks about the exact same as if we would have actually fixed that pH problem there. I want to show you some data behind this seed place phosphorus concept. And this comes from Clayne Jones at Montana State University, who's been doing work on both of these issues because they got it just as bad as anybody else, if not worse. So this is a trial where they applied different rates of phosphorus with the seed, and they also had a limed comparison. Now the initial pH at this site was 4.4, so very acidic. Now you'll notice that the Olson P and Bray P tests were both at 48 and 105 part per million. So this site was loaded with phosphorus. I mean, it had plenty of phosphorus that we would think about. So when we're adding phosphorus in this case, it isn't to provide more phosphorus fertility. What we're doing here is we're using phosphorus as a very expensive liming product to manage aluminum toxicity. And you'll see as that seed place phosphorus rate increase up to 20, 40, 60 pounds, they actually got as good of a durum yield as they did with putting on 5 tons of egg lime. So in this case, this phosphorus Band-Aid worked actually quite amazing. Now, I will say putting on 60 pounds of P2O5 is quite expensive, especially at current phosphorus prices. Here's another site. Did the same experiment, but we don't see this beautiful curve here. Here we got a case where the phosphorus and the lime, it didn't interact in the same way. So in some cases this works, some cases it doesn't. Here's the economics on this same set of experiments. So the break-even point right here at 0 is about here, and the net revenue in this circumstance, if you did not want a lime, was maximized somewhere around 60 pounds of P2O5. So with in spite of fertilizer costs, which actually Clayne's numbers here at 50-cent phosphate, it's actually a little bit outdated. You had maximum ROI. But in this other case, where you didn't have this nice curve, applying more phosphorus was actually a net negative revenue, or what we call it, a financial loss. So what do you do in these circumstances? Well, Clayne's advice here, and I fully agree with him, is we have to do field strip trials where we go out and actually increase some phosphorus rates in certain parts of these fields and seeing if we can actually use it as a Band-Aid treatment. So, yeah. All right. So let's summarize a lot of things that we've been talking about today. We do know that acid soils are becoming more common, and if you have pHs that are in the 5 to 5.5 range, you need to be very concerned about aluminum toxicity. And even if you're growing legumes, pH is up at 6, 6.5, you're going to have reduced nitrogen fixation. We also have to remember that these soils are going to continue to acidify over time because we are still using nitrogen. There's no getting around that part. And you can use acid-tolerant varieties and seed-placed phosphorus as a short-term solution, but liming is really the only true fix to change soil pH over time. And another good thing, if you have acidity that's concentrated near the soil surface, liming without tillage can be an effective option in no-till systems. Got this graph here to again remind us of this upward trend of soil acidification. This isn't going to be something that's going to go away. It's only going to become more common. But you might have more questions, and I fully understand that because we can only discuss and cover so many things in an hour today. What if you have acid-tolerant varieties that you've already chosen, they're not going to grow? You know, how much is that lime going to cost? Where can you get it? What kind of equipment is needed? You know, the question about owned land versus rented land is very important. I think of liming as a capital investment, just like anybody investing in tile drainage. You know, it is a capital investment meant to last 5, 10 years. It's not going to pencil out in the first year, but over the long term, that's how you have to think about this problem. And if you don't want to do any of those things, then we have to think about alternative land uses, such as pasture, hayland, or in some cases CRP. It's what we've done with salinity management, and I think it applies just the same here. So with that, that's where, oh, you're probably wondering about why did we call this Toto? I think we're in Kansas. All these discussions about acidity is very much like the Southern Great Plains, and sometimes we do feel a little bit like Dorothy, I think. Thank you all.
If anyone has any questions, let's ask them now, and then, John, do you want to repeat them?
Yeah, I certainly can. Yes, sir.
On our soil tests, do you automatically take into account on the subsoil?
Okay, so the question was,
On our recommendations, I don't think you did, but I just wanted to clarify, I guess.
yeah, the question was on the egg by soil test, if you have a high subsoil pH, does that automatically get factored into adjusting the lime rate guideline? And no, it does not. So that's where that comment comes in, and you have to look at that again.
Okay, if we have a soil pH of 5 or like 5.5, we correct it, what percentage of yield gain are we going to get from that? Are we going to get like 5% yield gain at 5.5 pH up to 6.5, or what are your thoughts?
And so the question was, so if you have a pH around 5, you increase it to say 5.5 or 6, what is that yield gain going to be? That comes back to that graph with the different soil pH tolerances at different pH levels. So if you're at like a pH of 4.8 or 5 and you have a 30% yield loss, if we can address that aluminum toxicity issue and also increase nutrient availability, I mean, you should at least get like a 20, 30-ish% yield increase. But because pH affects so many things, you can't just look at it in terms of yield. You have to think about nutrient availability as well as weed control, because that's something we haven't talked about at all. If you have a crop stand that doesn't do well because it has a problem with the acidity issue, and if you have weeds that are growing up in and around that, I mean, that's a whole weed competition pressure as well, and how that affects that. So it's a loaded question, and I'm going to give you a loaded answer in return, but we do know from all of these individual components that if you increase and correct that soil pH, the benefits are manifold.
Water treatment lime, sometimes there's soda ash mixed in there. What's your thoughts there? I mean, because then you can get too high of sodium levels if it's applied, or?
Yeah, so the question with water treatment limes with using soda ash, which would be sodium carbonate, bicarbonate there. And the concern is about some of these other things that come along, like do you have too much sodium that's getting put on? That's where I would look at the sodium loading rate, because some of these soils, you can probably toss some sodium out there and it's not going to cause any soil structural issues up into a point, right? And that's where we soil test just to make sure we're not applying too much of anything in particular. Most of the water treatment lime or sugar beet lime, we often get questions is like, are there any heavy metals or things like that that we need to be concerned about? The general answer to that question is no, because it is water treatment lime on the human consumption side. So it's before you and I drink that water that this lime is being softened. It's not wastewater treatment where you start to get more funky stuff into those lime sources. So they have to use good quality lime on the intake process, and that's what they're using as a byproduct later.
So, would fertilizer use be the main reason why our pHs are dropping?
So the question was, is fertilizer use the main reason why pHs are dropping? So a couple things. Some of these soils have been naturally acidic for a long time. You talk to some of the old soil mappers, there's fewer and fewer of them left, so if you find one, ask them questions. And they'll be like, oh yeah, we knew there was acidic soils there long ago, but we just haven't really recognized it. So some of them started off naturally acidic. The nitrogen fertilizer, or the fertilizer use part, is really one of the big drivers, but also higher crop yields over time and removing base cations year after year. So you got the inputs and the outputs there, both kind of pushing towards acidification. And then in the no-till system, where we're starting to concentrate some of that near the soil surface, that just amplifies it even more. Did you have another question?
Yeah, I did, yeah, go ahead.
Long-term perennial in rotation, can you pull up lime down below?
Yeah, so there's a question about using long-term perennials in rotation if you can actually pull up lime from below. So what we're trying to leverage there is nutrient uplift. So you have a deep-rooted grass that can acquire some calcium and such down low, bring it back up to the soil surface, and then deposit at the top and change some of these mass balance things. You got to do the numbers on it, and frankly, I think in our lifetimes, it's too slow of a process. Especially, so I mean, you can have like perennial native vegetation systems, like where you like where they're doing it constantly, but you're leaving the residue in place. So there we are not having any crop removal, right? The other thing that system doesn't have is nitrogen inputs, which is again is really kind of the big driver there. And I think when you look at some of like native rangelands, again, like looking back at old soil survey data, some of those pedons that were classified and tested back in like the 1930s, 50s, 60s, they have acidic topsoils as well. And so even in our native grassland systems, soils always have this tendency to acidify over time just based upon losses from the environment and, again, rainfall coming into the system. So there was a clay mineralogist who really did a great job of summarizing a lot of what we do in agriculture. And he said agriculture is synonymous with disequilibrium in soils. So we're always adding and subtracting things in agricultural production. So anytime that we're introducing acids, exporting nutrients, one way or the other, there's always some kind of disequilibrium in there, and that is soil change happening over time.
Well, I guess you left off, how about crop residue breakdown? How much does that reduce?
Oh, question was about,
We get that mat of residue laying on top.
yeah, the question was about the breakdown of crop residue and how that acidifies soils with organic acids. I don't have a number to give you, Rick, but we do know it's a process. Now, one of the other cool things about no-till systems, we talked about this aluminum problem right near the soil surface, and if you have more organic matter concentrated there, organic matter actually complexes with aluminum and keeps it out of the soil solution. So where we have soils with more organic matter, that actually does bind up with some of the aluminum and helps mitigate the problem. George, how are we doing on time? Oh, okay.
You talked about soil aluminum levels. How about tissue testing for aluminum levels? And I've seen them go really high before. I wondered.
Yeah, that's a really good question. The question was about, what about plant sampling for acidity? And generally, I don't find it to be the most useful thing. Now, you can see in plant tissues that if there is more aluminum, they will take up more aluminum. But because aluminum toxicity is kind of a root level issue, there are multiple ways that plants try to deal with it. One of those ways that they deal with it is by trying to exclude aluminum uptake into the plant. So that's one way that they kind of mitigate it. So if they're trying to exclude it from the plant, then they're not going to have as high of aluminum in the plant tissue. But other plants, if they do take up aluminum, they will have ways to physiologically manage aluminum inside that plant. So when it comes to toxicities, plant tissue data is not as helpful because depending on the variety and what traits they have, they might be trying to mitigate that problem in different ways. So I always find that soil sampling tends to be the most helpful tool in diagnosing these issues. Manganese is a weird thing, so I could be here all day. Manganese is a cousin of the aluminum toxicity problem. So manganese is an essential nutrient needed for plants to live their life and complete their life cycle, but it can also accumulate at toxic levels. And because plants don't have as strong of a way to mitigate, or I should say manage manganese uptake in that fashion, if you see manganese toxic plants, the manganese levels will be extremely high in plant tissue, like 600, 700, 800 plus part per million, compared to an area where things are fine and dandy, that's maybe only 150 or something like that.
Should liming be looked at as a one-time treatment or a routine maintenance?
Question it was, should liming be looked as a one-time treatment or continued maintenance? And I would say yes in parts. So when you're going to go out to lime, the reason why we talk about doing it in tons per acre is you're going to put out a big jag of lime right away because that generally increases our pH and we're going to be able to recoup the increases in yield over a longer period. And typically, most lime applications, we're structuring them so they would last at least, like, say, 5 to 10 years. But then in another, say, 5 to 10 years, if the pH has dropped down again, then you would think about doing it again. So in the I states where they're more familiar with it, they're kind of locked into liming about every 4 to 5 years. But also with their nitrogen rates and rainfall, they're acidifying at a much faster rate than we would be.
Any more questions?
I will be around through lunch, so feel free to pigeonhole me in a corner and we can definitely talk about this more. Thank you very much.